Hello, my name is Millicent Warner and I will be presenting my Lab Before video on circuits and capacitors. First, let me go over the schedule for the video. I will start by introducing key ideas, formulas, and data from the experiment. I will then complete Part A and Part B of the lab. Afterwards, I will find experimental data and show my graphs and analysis. Lastly, I will answer the discussion questions: what if we used an actual ammeter instead of an ideal simulated ammeter? And what if we used a real battery to charge a real capacitor with no resistor in the circuit? The fundamental principles new to this lab, before I get into calculations, all have to deal with circuits and their components. Firstly, I will go through two of the most important rules, the loop rule and the node rule, on the next page. There, I will also cover the formula for Ohm's law. All of these equations are justified by the conservation of energy and charge. In this lab, we will be dealing with two types of special circuit layouts: series, where components are aligned one after the other, and parallel, where the components are arranged in almost a ladder dynamic. I will be using batteries, resistors, ammeters, voltmeters, and capacitors for this virtual lab to create different circuitry scenarios. One of these scenarios will be a special kind of combination, a resistor-capacitor, or RC circuit. We will assume that these are in quasi-steady state, or in other words, we will work out equations as if they were in steady state. The loop rule states that the sum of the potential differences equals 0, and the node rule states that the current entering a section of wire equals the current leaving the section. We will use Ohm's law to calculate in-between variables, and the formula is the potential difference equals the current times the resistance. I then state some more complex formulas, including those of a capacitor's potential difference, a capacitor's capacitance, and a formula to calculate the RC. Now let's go through the procedure for Part 1 of the lab upon installing Java and downloading the circuit construction kit. The first circuit we will make will have two 1.5 volt batteries, a 47 ohm resistor, a 100 ohm resistor, and two ammeters arranged in this manner. Using Ohm's law, we predict our current output to be around 0.0204 amps, which it is. As you saw, the ammeters read 0.02 amps. If we reverse the ammeters, the reading would be the same in magnitude but opposite in direction, giving negative 0.02 amps. The main difference in this next open circuit example is that one of the ammeters is replaced with a voltmeter. Looking at the electric potentials within the circuit, we will see that there would be a 3 volt potential from the batteries and a 0 volt potential from the resistors. We expect, therefore, that the voltmeter would read 3 volts, and it does exactly. Notice, however, that there is no current flowing, as the voltmeter has an infinitely large resistance. Take a look at the following list of potential differences. We only have differences with a magnitude above 0 between checkpoints A and B, C and D, and E and F. For a sanity check, we can plug these values into the loop rule and confirm that the sum of these values equals 0. And here is the graph showing these changes in potential difference. Notice how everywhere else, then, the intervals I mentioned has a 0 slope, indicating no change. Now let's observe the effects of placing one of the ammeters in parallel with the 100 ohm resistor. Because less current comes in contact with this resistor, we expect the current to be greater than the original current, or 0.02 ohms. Indeed it is, reading 0.06 ohms. We can also explain this phenomenon by recognizing the inverse relationship between current and resistance in Ohm's law. As resistance goes down, current goes up. Let's calculate resistance using these current and potential difference values as well as Ohm's law. In the wires and the ammeters, we find that there is 0 resistance, indicating ideal components. The 47 ohm resistor, however, has 48 ohms by calculation, and the 100 ohm resistor has 102 ohms. The red ammeter values were truncated very closely to the decimal, so observed resistances are slightly different than calculated. Moving on to Part 2 of the lab, where we will observe RC circuits consisting of a resistor and a capacitor, we will need a 9 volt battery, a 10 ohm light bulb, a 20 ohm light bulb, and a 200 millifarad capacitor. First, let's charge the capacitor. Current in the setup is the highest immediately after closing the circuit. It took me 10.2 seconds to get to 10 ohms and 19.5 seconds to get to 20 ohms. The current exponentially decreases as the capacitor is charged, eventually reaching 0 amps. To discharge the capacitor, we will use a different setup without a battery. We see again that the current is the highest immediately after closing the circuit, and it exponentially decreases as the capacitor is discharged, eventually reaching 0 amps. We discharged the 10 ohm light bulb in 13.9 seconds and the 20 ohm light bulb in 27.6 seconds. Note that the current flows in the opposite direction. Based on my time-dependent data collection, I want to find the capacitor time constant, or the time for the voltage to significantly change. As you can see here, we can plot the natural log of the voltage divided by the voltage at time 0 and set this equal to negative t over RC. After plugging in our slope, we find that our RC value is equal to 7.022 seconds. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about the real ammeter, and how would it have affected the circuits you hooked up to it? We are assuming our ammeter is ideal, but real ammeters have resistance. Therefore, our observed values in real life would be less than those from a simulator. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? If there is no resistance, the capacitor would reach a full charge in an instant. This would not happen in real life, as all components of the circuit, even wires for example, exude some resistance. In other words, any resistance indicates some time involved. Thank you for watching.